Okay, today we're going to look at the rates of change. So we have what we've worked with before, which is the average rate of change, which is in this box, and we have the notation delta y over delta x. That's just change in y over change in x, or the slope. And then we have the notation where we introduced f of x minus, last year I think we called it f of b minus f of a divided by b minus a. So that's just your average rate of change. We're just replacing those b's and a's with x's in this case. And then below that we have the instantaneous rate of change, which is found by taking the derivative. And so these are all equivalent statements. So each of those represents the derivative. So those are just different ways to write it. And if you look at that, the average rate of change and the instantaneous rate of change is just taking the limit of the average rate of change. Okay, so what does the average rate of change represent graphically? Well, graphically, here's a little sketch of this. If we have a function like that, then the average rate of change, let's say that we have a point here. No, yeah, that's good. And a point here, and we draw a line between them. That is the average rate of change, and that's graphically, what does it represent? It's the slope of the secant line. Okay, so that was from last year. The instantaneous rate of change graphically, if I draw another rough little picture, and we choose 2 points on this, let's take it, doesn't really matter where I'm at with that. Nope, not 2 points, 1 point. So the instantaneous rate is just the slope of the tangent line. So the tangent line is a line that touches the function at a point, at a precise single point. It does not go through 2 points. Okay, so let's look at some examples here. So let a equal pi r squared be the area of a circle of radius r. Compute dA dr at r equals 2 and r equals 5. So this is just using a different notation. This is Leibniz notation. We've been using f prime, which is Newtonian. So dA dr, to compute that, we would just have to take the derivative. So we're going to take the derivative of the area. So if the area equals pi r squared, then dA dr would just be bringing this 2 down, subtracting 1 from that. And just remember, pi is a constant, so it stays as it is. And then it says compute these two. So the notation for that is always, I don't really like this notation. Computed at r equals 2. That's simply 2 times, oh, I don't like where I put that. 2 times pi times 2. So that would be 4 pi. To calculate at 5 would be dA dr evaluated at r equals 5, which is just 2 pi times 5. So what those represent is the rate at which the area changes with respect to the radius. So that's what that would represent. And another way to write that would be the rate at which the area changes when r increases. I'm gonna write that statement right here. That's the rate at which the area changes when R changes. Okay, for part C, why is dAdr larger at R equals 5? So why is the rate at which the area changes larger or higher at R equals 5? Well, area of a circle, it's increasing uh, as R is squared. So the larger the R value, or the larger the radius, the faster the area is going to increase. So dAdr is larger at R equals 5 because it's a larger radius than R equals 2. Okay, so the area increases at a higher rate the larger the radius. So with rates of change, we start to get into some more application-based problems. And so one of the big things we work with is linear motion. So linear motion is motion along a straight line. So if S of t denotes the position or distance from the origin at a time t, then velocity is the rate of change of position with respect to time. So if you have a position function S of t, and you take the derivative, then that will be velocity, which is ds dt. So the sign indicates the direction of motion, so that we're talking about positive or negative. So if S of t is the height above ground, then a positive v of t value indicates that the object is rising. Speed is the absolute value of velocity. So speed is not a negative number. So that's why we take the absolute value of velocity. So here we have a problem. So this is the position of a car as a function of time. So the height of the graph represents the car's distance from the point of origin. The slope of the tangent line is the velocity. So this is the first time we've really worked with this type of problem. So let's answer these questions. First one is find an interval where the car is speeding up. Okay, so you have this graph here. The car is speeding up when it has a positive velocity. And that means that the derivative is positive, or the slope of the tangent line is positive. So if we look at this graph, if we were to draw tangent lines right here, we actually draw a tangent line. So if I have a tangent line, something like that there, you can see that it's a positive slope. So that would hold for everywhere where the graph is increasing up to about here. Okay, so for an interval where the car is speeding up, one of those intervals is from 0 to 2. Okay, so let's look at another one where it's speeding up. If we look at the from 3 to, what is that, 3 1/3, that would be another one. And at this end right here, this is another place where you'd have positive tangent lines. So anywhere where the slope of that is positive is where the car is speeding up. Okay, so find an interval where the car is standing still. So these questions, you get used to them as you do a lot of them, but it's speeding up when the rate is 0. And when the rate is 0, we have tangent lines that have slopes of 0. So anywhere you see a flat section in this, this is where the car is standing still. So in this section here, from 2 to 3 would be an interval where the car is standing still. And there's another one right around here. So anywhere we have 0 or tangent lines with a slope of 0. Okay, still using that picture, is there an interval where the car changes direction? So remember that negative velocities, that's a change of direction, so it's going the opposite direction. So in this, we do have one little section where it changes direction. So you can see that the slopes were positive here, 0 here, positive here, and you have another peak. And then in this section, when you see the slope of that line would be negative. So that's where the car would be changing direction. It's going the opposite direction then. So I would say somewhere in the interval from 3 to 4. I'm not saying for the entire interval, I'm just saying somewhere between 3 and 4, it changes direction. Just trying to avoid decimals and stuff to make it a little easier. Okay, so let's look at another problem. A truck enters the off-ramp of a highway at time equals 0. Its position after t seconds is s of t equals 25t minus 0.3t cubed meters on the interval from 0 to 5. So how fast is the truck going at the moment it enters the off-ramp is the first question. So this graph is telling us the velocity. So this is not a position graph like the last one. This one is the velocity, meaning that we're no longer looking at the slopes on this graph. We're actually looking at the function values because it says it's a velocity graph. So just to be clear, if I back up to the other problem, this was an S graph, S of t, or a position graph. Okay, so how fast is the truck going at the moment it enters the off-ramp? Well, it is just whatever the function value is. So right here, that's v of 0, and that's 25. So that's meters per second. Is the truck speeding up or slowing down? Well, that's saying, are the function values increasing or decreasing since we're looking at a velocity graph? Well, we can see that it is slowing down. Again, that might seem obvious, but we're just looking at, these function values are decreasing, so its velocity is decreasing on that interval. Okay, so we're going to look at Galileo's formulas. These aren't used all the time. They might not even show up in other examples, but they're a good place to start with position and velocity. So S of t represents position, and v of t represents velocity. And just to be super clear about this, if you have S of t and then you take the derivative of it, then that is v of t. So those are interchangeable. And while we're here, even though we don't really need it, if you take the derivative of v of t, that is acceleration. So those are equivalent statements. And what we're really looking at is just these parts. And it gives us the gravity. Okay, so a stone is shot with a slingshot vertically upward with initial velocity of 50 meters per second from an initial height of 10 meters. Find the velocity at t equals 2 and t equals 7 and explain the change in sign. So what we're going to do is take this v of t, and I'll just copy the formula. So v sub 0 is our initial. And let's plug in the stuff that we can. So v of t is our initial velocity, which is just given to you as 50. And then gravity is 9.8, and you have t. So that one's just to really plug in the numbers. So v of 2 equals 50 minus 9.8 times 2. You get some approximate number around 30.4 meters per second. And let's look at v of 7. So 50 minus 9.8 times 7 is approximately negative 18.6 meters per second. All right, so it says explain the change in sign. So at v of 2, we have a positive sign for velocity. So this would be rising. Okay, for v of 7, we have a negative velocity, so this is falling. So you'd have a graph. If I were to just draw a little graph, it's something like that, because an object is shot up and then it goes to a peak and then it falls down. So we would have positive slopes over here, negative slopes on the other side. So it's going to rise up to a point, it pauses instantaneously, and then it drops. And so those negative velocities are when it's falling. Okay, next question. When or what is the stone's maximum height, and when does it reach that height? Okay, so the maximum height is going to be when the velocity equals 0. So I'll write that, zoom in a little bit. This is really asking, where does the derivative, or v of t, equal 0? Okay, so we take the derivative, which is v of t. So again, the derivative of s is v of t, and we set that to 0. So we're going to go 50 minus 9.8 t equals 0. And then we subtract 50, divide by negative 9.8, and we'll get t is approximately 5.1. Okay. So this question, the way it's asked, is actually backwards, because what is the stone's maximum height and when does it reach that height? Well, with this question, we have to find when does it reach that height to find out what it is. I'm just going to move this over a little bit. Okay, so now we're dealing with the other formula there. So this one is the velocity is where we got our time at which, so that's the time of the maximum. And then let's look at our position graph. So, or not graph, but equation. So S of t equals your initial position plus initial velocity times time minus 1/2 gravity times time squared. Okay, let's fill that in with the stuff that we know. So S of t equals the initial position, which is 10, since it was at an initial height of 10 meters, plus our initial velocity, which was 50, t, minus 1/2, gravity is 9.8, and then we have t squared. So that is the setup for position. So then we just need to see the position at t equals 5.1. Okay, so this comes out to around, need to adjust that a little bit. Should say S of 5.1. So this comes to approximately 137.5 meters.